Okay, today we're going to talk about motion. So first we need to define motion. So before we can define motion, we're going to define position, a place in space-time. So this gives us a chance to talk about Monsieur René Descartes. He came up with something called the Cartesian graph. So let's look at that Cartesian graph. So we will go back to our regular screen. And we will see that if we had a map, and on that map we'll say, here is building A from above, and let's say this over here is building B. A puts us in a position relative to B, and then we can walk, let's say, in a straight line, assuming that's a straight line, to building B. Okay, we all understand this concept. So what René Descartes did was he put it in terms of something called a Cartesian graph. So let's look at y-axis, and let's look at the x-axis, and let's imagine coming out of our screen a z-axis for three-dimensional space. And this represents the Cartesian graph. Now, we're just going to use the Cartesian graph in the sense of two dimensions for this particular discussion. So we have our y-axis and our x-axis, and this is our point of origin. So everything below this point of origin is negative y, and everything to the left of it is negative x. So negative 1, 2, 3, 4, so on and so forth, positive 1, 2, 3, 4, and so forth, negative 1, 2, 3, and so forth, positive 1, 2, 3, and so forth. So, in order to understand position, we need to understand something called ordered pairs or coordinate. So if I said this is 1, 2, 3, 4, and then I evenly space 1, 2, 3, 4, that's pretty sloppy, sorry about that, but let's say we went over 3 and up 3, this would be our coordinate. If we then went to the position that was over 4 and up 2, this would be our new coordinate. And we can see that we can build up these coordinate systems, and we can collect data, and we can see how it behaves graphically. But this is, for physics, in this particular physics lesson, we're going to talk about the Cartesian graph from the perspective of giving us position, okay? So that's what we mean by position. We have a coordinate that we triangulate based on 2 dimensions or 3 dimensions, okay? That's all that refers to. So those are called our ordered pair, and we'll think of our ordered pair as x, y, or x, y, z. But that would be not a pair, but a 3-dimensional coordinate. So again, let's just focus on x, y for the first lesson. So these are our ordered pair, and that's how they'll be presented. So I might present to you negative 3, positive 5, okay? So then in that case, I would look at my graph, and I would say that I am going to treat that as x, and that is y, because that's the convention for ordered pair. X comes first. And I would say there's negative 1, here's negative 2, here's negative 3. So I'm going to move to this position. I'm then going to move up positive 5. So 1, 2, 3, 4, 5. Here's my coordinate, my coordinate right there. Okay, that's what the Cartesian graph's all about. That's the gist of it. Now, let's talk about speed and velocity. Now that we've talked about position, we can talk about moving from one position to another, and in so doing, we're going to talk about speed and velocity. So last chapter we talked about velocity is equal to distance per unit of time, which is equal to meters per second. So if I say something is 10 meters per second, I see that's a unit of velocity. And it's easy to remember the formula because I'll almost guarantee if I said 10 meters per second, you would understand that as velocity, or speed or something like that. You would understand it's a concept of traveling a distance per time. But then if I say, well, what's the formula for it? They'll pause and they'll think about it. Well, you just said 10 meters per second. The formula was given to you. Right? Right? It's right there. So yeah, just relax. You know this stuff. And remember that you know this stuff. It's just, it comes down to an issue of staying calm and realizing everything, this is the rule of thumb, everything's easier than it looks. So, scalar. Scalar is a quantity, okay? It's a quantity that does not have direction. So, it's magnitude without direction. So, vector is magnitude with direction. So, if I'm speaking about velocity, then I'm talking about something that is a vector quantity, and this will be put over, so if I said it's 10 meters per second with this, that lets us know it's a vector. Okay, it has a specific direction. Okay? Scalar is speed, and it doesn't concern itself with what direction you're traveling. So, you don't need to be in a straight path, you can travel a changing path. So, these are a series of changing velocities because we're changing direction, but one speed. Okay, so scalar is speed, vector is velocity. And since acceleration is equal to a change in velocity over a period of time, we see that it is also a vector. So let's clear the whiteboard. All right. Let's talk about average speed. So average speed is going to be equal to the distance traveled and the time it took to travel that distance, okay? So we see that it's being interoperable as average velocity here, right? The main thing to remember is that speed when identified, we're not concerning ourselves with direction, but if I specifically identify it, or any physics question or teacher or situation identifies it specifically as velocity, then we're concerning ourselves with direction. Okay, let's look at instantaneous speed. So instantaneous speed, let's imagine a speedometer on a vehicle. So it starts at 0 and it goes up to, let's say, 100. So whatever that needle is pointed at any given moment, so let's say that's 45 miles per hour, right? That's considered the instantaneous speed at that moment, at that instant in time. Now, speed is not concerned with direction. So let's say I travel around a track, okay, and I start here, and then I end here. I'm going to calculate the distance I traveled, and that would then be my speed, where velocity is going to be displacement, not distance. So if I were calculating my velocity, I need a straight line. Displacement is represented by a small s oftentimes, and that is displacement. Now, not to be confused with seconds, it can be confusing at first, but you'll start to see the convention and use the context of the question to identify what they're referring to. So, in the context of the formulas. So you can see that displacement is a straight line. So again, let's say you start here, and you travel this direction. Speed is going to account for the entire distance around the curves. And if you stop here, where displacement, that's distance, where displacement is going to be a straight line to where you ended. Okay? This would be displacement. Okay? So velocity needs to be concerned with displacement, not distance. Where distance is going to be concerned with speed. Again, speed doesn't concern itself with direction, it's scalar. Velocity concerns itself with direction, it is vector. Okay? That's the main thing to understand. Alright, we're going to leave off right there, and it looks like we will pick up with a practice problem on the next video. So if you're interested in doing a finding speed and velocity practice problem to kind of get a handle on that, go ahead and tune into the next video, and have a pen and paper ready, and then you can, feel free to take that problem, manipulate, change the values, whatever, and use them with your class, and start to build up that repertoire with the basic sciences to help your junior high school students get a better handle on the physics and the chemistry and the math involved. So that was kind of a weird rant, but blah blah blah. Alright, welcome back to fuzzytutor.com. As promised, we're going to do a find speed and velocity problem. So I went into one of my old physics books and I found a good problem for us to practice. So we have a diagram, and I'm going to pause this while I draw the diagram. Okay. So, this is the diagram given in the book, and this is just a stop motion of this car traveling. So this is at t equals 0 seconds. This is t equals 1.0 seconds. This is t equals 2.0 seconds. This is t equals 3.0 seconds. And this is t equals 4.0 seconds. And these arrows represent 20 meters of travel. 20 meters of travel. So, up here on the whiteboard you can see that we have this fairly easy to understand diagram. And now what it wants us to do is describe the motion in terms of speed and velocity of the car in this particular figure. So, isolate known terms. That's step 1. So step 1, isolate known terms, IKT. So our known terms here is total distance equals 80 meters. We can see that here, right? 1, 2, 3, 4, and each one is a value of 20 meters. We simply 4 times 20, and that gives us 80 meters, right? 4 times 20 meters, there we go. So we have a distance known, isolate known terms, distance known, 80 meters, okay? We have known time, t equals 1, right here, 1, 2, 3, 4. So we have 4.0 seconds, and it's written right here, right? So, we have d and t, right? We know their values. So, let's look at our fact family. So before we do that, let's isolate needed data. What's our needed data? Okay, they want us to isolate speed and velocity. And we're going to use the same formula to solve both of those. We're assuming it's a straight line because it gives us no indication otherwise. So, isolate needed data, right there. Now, let's determine a course of action. Alright, DCA, determine a course of action. So, what's our fact family we have available? Alright, we have D equals 80 meters. We have T equals 4.0 seconds. And then we need speed, but we're going to just write velocity. We need velocity, okay? Velocity equals D over T. This is a pretty no-brainer kind of a problem, so we go 80 meters over 4 seconds. And does that look like meters per second to you? Because it sure does to me. So we know it's going to be 80 divided by 4, which is going to come out to 20 meters per second, right? 20 meters per second, or 20 d per t, right? As we established right here, right? Same thing. So, Note that the car has a constant uniform speed and travels 20 meters each second. If the motion is in one direction, a straight line motion, then the car's velocity is also constant and is 20 meters per second in the direction of the indicated motion, which is right there. And that's all they give us, so we're going to assume that that's the case. So step 1, IKT, step 2, IND, and step 3, DCA. Step 4 is solve. There we go. All right, that's our first practice problem. So that one's pretty easy, but they really all are. We just have to take them for what they are, examine the components, look at the formulas as though it's communicating to us as a spoken language, as a normal language, and just see what it is it's trying to tell us. Okay. Now, the next one is finding the time it takes for sunlight to reach the Earth. Whoa, that sounds crazy. No, this is really easy. The speed of light in space is 3 times 10 to the 8th meters per second. So they give us some information. 3.0 times 10 to the 8th. And here's that scientific notation we talked about, right? Meters per second. Right? It's a constant. This is the equals c. So when you see E equals mc squared, this is the c that they're talking about, is the speed of light. So energy is equal to mass times the speed of light squared, okay? The very famous Einsteinian equation. So the speed of light in space is 3.00 times 10 to the 8th meters per second. How many seconds does it take light from the sun to reach the Earth? If the distance of the sun to the Earth is 1.50 times 10 to the 8th kilometers, okay? I think we can handle this one here. So we have a distance, right, or a length measurement equals 1.5 times 10 to the 8th kilometers, right? Then we have a velocity, which is a derived unit. Velocity equals 3 times 10 to the 8th meters per second. Okay, and that is derived from length divided by time, right there. Okay, that's our velocity. That's what it's a ratio of length per time, right? So we have our fundamental units of length, time, and mass, which is kilograms, which I'll just put mass, length, time. Mass equals kg, length equals m, time equals seconds. And make a mental note here. We're at kilometers, not meters, so it's not in SI units at this point. So let's clear this out and look at it again. We have, so our known, isolate our knowns, and our knowns are velocity and distance. Velocity equals 3 times 10 to the 8th meters per second, and distance equals 1.5 times 10 to the 8th kilometers. Okay, so those are our knowns. Now, let's get D into some SI values here. So we have 1.5 times 10 to the 8th, 1.5 times 10 to the 8th kilometers over 1, that's what's given, right? And what we want is meters, so we're going to get a conversion factor going. So 10 to the 3rd meters, right? 1,000 meters is 1 km, right? We get that diagonal going I was talking about in the conversion factors video. Revisit that if you need to. So we give what we're given and put it over a value of 1, so that a denominator of 1. So we have 1.5 times 10 to the 8th kilometers. Put that in parentheses. Next we put in parentheses what we want, meters. And then we put a ratio of this measurement up here, right? And here. So we put that diagonal. So we take this measurement, put it here, give it a value of 1, and then the ratio of what we're looking for. We're looking for meters. So what's the ratio of meters to kilometers? It's 10 to the 3rd or 1,000. So that's what goes there. So we end up with 1.5 times 10 to the 8th divided by 1, which is just 1.5 times 10 to the 8th, times 10 to the 3rd meters, right? We create the ratio of these kilometers to what we want. A ratio of what we have to what we want, right? Okay, so what we have becomes the new denominator at a value of 1, and what we need becomes the ratio of that as the numerator, so 10 to the 3rd meters, okay? Now we cross cancel, because it's right there, and multiply straight across as you do, and you have 1 times 1 is 1, 1.5 times 10 to the 8th times 10 to the 3rd, and we get 1.5 times 10 to the 11th, as we can see, and that is in meters. We simply add the two exponents together, and here it is. It is just that simple, guys and gals, or gals and guys. So here we go. 10 to the 11th, 1.5 times 10 to the 11th meters. So now we have converted kilometers to an SI unit of meters. Okay, so now we have just a couple minutes left on this video, and we're going to try and quickly solve that. So, what is wanted is t, which equals time, for the light to travel from the sun to the earth, which is what the question establishes. If we rearrange for the unknown t, we have t equals d over v. So, we can establish that t equals d over v. And again, let's look at v equals d over t, multiply t, and divide away v, and you get, and then you gotta do it to this side, and you get t, whoops, and you get t equals d over v. So that's where that comes from right here, okay? Just a quick reminder. So then we have d is equal to 1.5 times 10 to the 11th meters per velocity, which is 3.0 times 10 to the 8th meters per second, right? And then, of course, the meters cross cancels, and cross cancels, all that's left is seconds, so we know whatever this comes out to is a unit of time, right? So t equals, and you can carry out the math, and it comes out to 5 times 10 to the second, 5.0 times 10 to the second seconds, and then that equals, of course, 500 seconds. And there you go. And that puts us at about 11:50 into the lesson. And now these lessons are going to be shorter because once everything's cleaned up and chopped up, it'll be a little bit shorter because I have to reduce it down for YouTube where these are viewed. So thanks for coming to Fuzzy Tutor. We're about out of time on this particular video. So cheers.